This work is interactive rate supervisory control for arbitrarily routed multi-tendon robots via motion planning. This is a tendon-driven robot, a promising type of continuum robot. Tendon-driven robots have a flexible backbone with tendons routed some distance away from the backbone. By applying tension to the tendons, we can actuate the robot. With non-straight routings, we can achieve interesting shapes, as seen here. However, kinematic modeling is computationally expensive. Tendon-driven robots may potentially improve minimally invasive surgeries, from their ability to curve around anatomical regions and access difficult-to-reach sites. Their flexibility adds inherent compliance, which improves safety near these sensitive anatomies. This picture shows a collapsed lung on the left, with the black region representing the empty pleural cavity. We envision a clinician inserting the tendon-driven robot into this empty cavity and guiding it with specified tip positions as a motion planning system visits each specified tip position with collision-free paths. Because of the expensive kinematic model, current approaches take about 20 minutes per plan, which prevents interactivity with the clinician. Our motion planning method is divided into 3 phases: precompute, load, and supervisory control. The precompute phase randomly samples many configurations and connects them together to form a roadmap suitable for planning. For each configuration, this roadmap stores tip positions and the robot's voxelized backbone shape. Here are 10 example robot shapes from the set of 30,000 tip positions on the left. For the edges connecting configurations on the graph, we precompute the voxelized swept volume of the motion between connecting configurations. Roadmap precomputation is done without knowledge of the anatomical environment and only needs to be done once per robot design. In the load phase, we load the anatomical environment and precomputed roadmap and prune away in collision vertices and edges. Anatomical regions that are segmented from 3D medical images, like this CT scan, are already represented as voxel sets. Loading and pruning our roadmap is very efficient, taking less than 1 second for our roadmap of 30,000 vertices and 570,000 edges. The last phase is supervisory control. The clinician provides a desired robot tip position. We run our roadmap by K algorithm to generate a goal configuration. We generate a plan over the graph to the new goal configuration, execute that plan on the robot, and wait for the next desired tip position. Our roadmap by K algorithm first finds the nearest neighbors in the roadmap to the specified goal tip position, performs numerical inverse kinematics from each one, attempting to connect them to the roadmap. We keep the connection closest to the goal tip position and add additional lazy edges to nearby configurations. Having connected this found goal configuration to the roadmap, we generate a plan over the graph using the optimal and efficient A-star search algorithm. The plan is executed and we wait for the next desired goal position. Our contributions are 1. A much faster forward kinematics model that is 1,100 times faster. 2. A fast voxel collision method that is 28 times faster than mesh checking. And 3. We leverage a pre-computed roadmap to improve the speed and quality of planning. We achieve an interactive rate at 15 Hz on average. Compared to other popular off-the-shelf planners not using our contributions, our method can plan to 25 consecutive goals in less than 2 seconds, whereas the best competition accomplishes the same feat in nearly 9.5 hours. Our method achieves a 17,700 times speedup over the fastest comparison. Here's an example of supervisory control with a haptic input device. The small sphere is the tip of the haptic device. The user clicks the button on the pen to set the goal to the current haptic tip position, as seen by a large sphere appearing. We can qualitatively visualize the planning time as the delay between the large sphere appearing and the beginning of the robot motion. Thank you.